verified that. Feynman rule same, propagator same, I epsilon same, right? Endpoint function same, interaction same, loop same, everything same. But then what's the point? Well, it does turn out to be helpful for some other things, and we will get to that in the later part of the course. But one thing that I can point out right now is that because in the canonical quantization way you separate the time derivative, the momentum and the variable, there's a p and there's a q. And so Lorentz invariance is harder there to keep track of. In the end, of course, when you calculate a matrix element, you find that it's dot product of 4 vectors, so it's all Lorentz invariant. But it's not clear in between what is happening. Here in the Lagrangian, you start with the Lagrangian, everything is Lorentz invariant all the time. Okay? So it's just manifest. The word is manifest. Okay. Another couple of comments. So I think I can erase this now.
So how did you separate the exponentials? You separate the L interaction out. How did you do that?
So
because
yes.
You are working with operators now.
No, but this is a path integral, right? So the files are just numbers over which they are integrated. So
okay, so
so it doesn't matter. And this is one of the nice things about path integrals. That you don't have to worry about this ordering now. Of course, there is an ambiguity in going from the Lagrangian to the path integral. What Lagrangian corresponds to the operator that you wrote, right? Because if you have, probably you might have you might have seen this, but if you have a term like a product of two operators which don't commute in the operator sense, and then you went to the path integral, you take this order or that order, right? Because in the path integral it doesn't matter. In the canonical quantization it does matter. So which one will give you the right answer? And anyway, so there are some tricky things there. I think sometimes you miss some kind of physics if you just take one order. But here it's not important. If you just a 5-4 interaction, compute with everything and do it wherever you want.
So for that, is that the while ordering that you have to do? Is that what that was?
The while ordering?
Yeah, and Heskin and Schroeder, they talked about that. Basically, you need to have something that looks symmetric in the operators because you can...
Oh, yeah. But I remember this was a problem in one of the other courses I had taken, that you sometimes have to consider a different ordering to get something. This was like this was in a condensed matter system, so it's finite magnetic. I don't know enough about it, so I just know that you have to be careful about it, and in some special cases it might be important to consider some other. Usually just take both orders and divide by 2. This is one way of doing it. I think that's what maybe the while ordering is. Okay, so now something very interesting. Those of you who have taken or who have experience on condensed matter or statistical mechanics will say, we have seen something similar to this. Okay, so let me, so e to the I to j, or the okay, so this is the next question from the, yeah.
When did we quantize this here? At this quantized rate?
We did, because we have made it a path integral now, right? Even for the case of a double slit experiment, when you allow amplitudes addition and when you allow everything to go, the intermediate values to go everywhere, this is how we derive path integral, right? How did we even come to the integration, come to this form? We started with quantum mechanics.
Yes, and then we were talking about C numbers.
Yeah, but
fields.
Yeah.
C numbers, but now suddenly we are saying that these are all quantum. These quantum fields.
They are quantum fields, but see, to quantize there are 2 ways: canonical quantization or path integral. One of them requires operators, the other requires C numbers. But the one which requires C numbers, which you would think, why is that given quantum? It requires C numbers in a weird way, right? You have to integrate over all intermediate values of it's like a path integral. You don't do path integral in regular classical theory. Like nobody calculates a electric field due to a point charge by path integral. So that's where we have quantizing. 2 ways of quantizing the path.
we started at operators. Remember the Heisenberg operator?
No, but if you started with the operators, then you can't separate an interaction.
No,
just
no,
like
no.
that.
Yeah. Well,
So while he did path integrals, he was taking.
We were calculating. So go back to quantum mechanics. Okay.
Yes.
What were we calculating? Do you remember? Yeah. Okay. Tell me, what were we calculating?
So we were calculating amplitudes and theirs.
Right. There were operators and kets and bras there. Right. We were calculating the amplitude to go from xi to xf.
Yes.
Right. And there was a Hamiltonian there, because that's how things evolved. And everything was an operator there, right? Agreed? Hamiltonian was an operator. These were states which are eigenvalues.
Yes.
Then we said, okay, let's just try to calculate it in some way, and then from that, starting with operators, we came to an expression which just involved integration over p, which was a C number, which was the eigenvalue of the corresponding operator, right?
Yes.
So we started with operators, we came to something. So you can't say that we never quantized in that sense. We are already starting with a quantum version because we are talking about calculating the amplitude for a process with operators.
Yes.
Now we are doing something to get to a form which does not involve operators. So it's not, we didn't just write it by itself.
No, but my only confusion is that you separated out an interaction, which
In this formalism, it's fine. As long as I am within this formalism, as long as I say that these phi's are numbers, or C numbers right now. I did not do that in the canonical quantization, for example, right? I just got the answer from canonical quantization.
But you didn't do that in quantum mechanics either. You inserted some states, and you knew how the operators act on these states. Here you did no such thing. You said that the manipulations assume that phi's are some C numbers.
Right.
And you manipulated to get this. But now you are saying that these are operators.
No, I never said these are operators.
But
I'm saying this is making sense from the expression you would get from canonical quantization. There is a way to calculate this in canonical quantization.
yes, it makes sense. But the way you derived it, you never assumed that these phi's are operators.
Right. Right.
the answer, I think, is at the beginning we were saying we're not going to repeat the derivation of how you get a path integral in field case, but it proceeds exactly the same way. You insert complete sets of states, you turn your operators into C-number fields. And so that kind of all happened behind the scenes. And so if you have an interaction, by the fourth interaction, just like before, it starts out as an operator, you insert complete sets of states, it becomes a field, and then it gets separated out in this way. So I think the only thing is we didn't repeat the same derivation because it's almost...
I mean, I think it should not be confusing at all. There are two ways of calculating the same thing. One is canonical quantization, which requires operators, which gives you all this machinery of Wick's theorems and so on. We're talking about operator ordering, right? You want to calculate this to normal order and so on, so that gives you the Wick ordering. The other way is a path integral. Remember, all we are saying is this expression, which is the endpoint function of some bunch of operators, is obtained by differentiating a C number with respect to a C source. This is a number, right?
Yeah.
Between some states, the expectation value of some operators. Yeah. All the path integral is saying is that you don't need to go through the path of operators to get the same answer. You can get the same answer by differentiating a function of C number with respect to another C number. Right? The answer that we had for this had no operators. Right? And it's all fine because in the end you're not even supposed to get an operator as an answer. It's an amplitude, it's a number, right? It's a C number for the process. So I don't think there's any confusion. I mean, the operators is one way, but the other way which we derive from looking at the operators does not involve operators. Yeah.
I think part of the confusion is that, when we've written this endpoint correlation function right here, this is just basically a coefficient in the expansion in J. And so when we wrote the expansion in J, we wrote it as a sum over powers of J with this endpoint correlation function and J x1, J x2. And so it's really just a C number coefficient in this expansion. And it happens to be identical to, in canonical formalism, it happens to be identical to this inner product thing where you have states and operators in the middle. So written like this, it kind of looks like you're saying, do this calculation with omegas and with the operator's phi and with the time ordering symbol, and you'll get this.
Yeah, so
But
what you're
it's
saying...
really kind of the other way around.
No, well, I think what you're saying is the following. So I think maybe this will clarify. So okay, roughly, this is what the story is. That side is from canonical quantization. It has states, it has operators, it has Wick, like the Wick ordering thing. What is it called? Wick's theorem thing, right? Change the normal order and so on. That is that side. That same quantity is to be obtained by differentiating a path integral, which is an integration over C numbers, with respect to J, which is a C number, that many times. That expression is given as this. It does not have any operators or any of the states, right? And this is the equivalence. Something which you calculate using operators, but in the end is a C number, is also obtained by just C numbers, but in a different way, which is the path integral. Does that answer your question? Good. So we were here, right? So we were here for the field theory case. Now this is to be compared with the corresponding expression for the partition function. So this is StatMech. So this is and I'm going to make it equilibrium time. So equilibrium means there is no time. Okay, things are not changing with time. And this is equal to sum over phi e to the minus sum over x. So I'll explain what it means. Beta h of phi or in a more familiar form, so the thing you are imagining here is the following. You have a bunch of spins, okay, from 1 to n, and the spin variables are S1, S2 up to Sn. So there are n particles with spin Sn. And the Hamiltonian is of course a function of the spins, right? And usually you probe such a system by switching on and switching off some external magnetic field. And you calculate the partition function by summing over all possible values of Sn. Okay. But you do e to the minus beta h, where h is the Hamiltonian, right? So this is you weigh everything in that way. So this expression and that expression are to be compared, This integral over d phi is effectively like summing over all phi's. This is like effectively summing over all Sn. The integral over x there. So of course, that's why I said equilibrium, because there is no t here. Okay, this x or this n, this corresponds to this. So there is no t there, right? So they look the same space. Anyway, so the point is they look the same, but up to, of course, you would say they're not really same. There's an I there, there's a minus sign in front of the exponential and so on. And so this is why I just have to mention this, that this I dt is actually this I dt over h bar in the quantum mechanical way, because we have set h bar equal to 1. And so you can compare that, and this beta is 1 over kt, right? So I dt over h bar becomes I dt is actually I dt over h bar, and this is equal to 1 over kd. So this is not to be compared, because you would say there's a dt here, there's no corresponding dt here, and so on. You're just supposed to look at the two expressions and see that they are very similar. And as instructed, I have to tell you that this is something which is used a lot, but it's not completely well understood. How is this connection? There is a rotating the time in such a way that you go to imaginary time, and then this sign from I, it becomes minus. And if you associate the h bars with the temperature and so on, so it all seems very suggestive that there should be some way, but first of all, I don't know enough about it to tell you as an authority. But and more than that, I don't think anybody is an authority. It's just out there. This is being explored. This is used all the time in a lot of in concurrent research areas of ADS-CFT and dualities, and black holes and finite temperature quantum field theories and equilibrium field theory. It's all there, but this is the starting point, because these two formulas look so same. Okay. They all look like e to the something, and you can then go from one to the other. And well, the only thing that is really useful here is that this J is like the magnetic field, and then you have really a picture in your head. You have a bunch of spin systems in some condensed matter experiment, and you switch on magnetic field from here, and you let them do something, and eventually they return to some state, and you read it by another magnetic field, because you want to read the spin. So this is what effectively our J has been doing all this time. Okay. So let's stop here.